Okay. So, for whatever reason, the other day, I got a mail from YouTube saying I now have infinite privileges to update, upload anything onto the network. I'm going to obviously live to regret this. So I actually, over 2 days, in the background, I uploaded every possible lecture video from here. And they're also all available, so they're all streamable, and they're available as a playlist. So, you can put it on your iPod, whatever you want. And then, the other good thing is that they're asking me to monetize this. So apparently I can put advertisements. So if you can tell me what kinds of products you would like to buy when you are watching A-Star Search or Bayes Networks, because you're my only customers. So, and I hope you'll buy a lot, and just let me know. I'll just monetize it. Okay. These guys are actually quite smart. In fact, I don't know whether let's see if I can sign this. They actually can tell. I never had to do this before, but anyway, that's fine. Later on, I can show you. But they were able to actually tell that the first one had copyrighted music in it. Do you guys remember what it was? Yeah, 2001: Space Odyssey. So they basically said, no, it does look like, it looks like it has copyrighted music. It's okay. We won't put you in jail right away. But if you try to make money off of it, then. So anyway, so that's the story. So we will keep these here. I guess the later ones also will come slowly, But it's easier for me to just throw in the videos as soon as I go up. So they'll always be available pretty much right away. That takes like 12 minutes to copy from the flip video recorder onto my hard drive. And then, as far as I could tell, it takes sort of 4 hours or so to upload this and process it in the background for YouTube. Anyway, so that's the story on that. And let's look at this. Tell me what you guys got. Okay, I can't write on top of that, but let's see. Is V independent of, by the way, if, I'm from Asia, okay, so I don't particularly like the fact that there is some reasonable connection being made between lung cancer, tuberculosis, and visiting Asia. So, so I didn't make it up, I just picked up somewhere. Anyway, so what about, so the V is V here. Is V conditionally independent of A given T?
Yes.
Yeah? Okay, why? Because if you consider the paths from here to here, okay, this is your evidence node, and there's only one path, and it's going through the evidence node, and it is essentially going with both the arrows, one going in, one coming out. So sort of a causal chain. And so it will be blocked if tuberculosis is given. Okay? So what about T? Is T independent of L? Is T independent of L?
No.
I didn't give any evidence. So basically, T independent of L, my question T independent of L means T independent of L given nothing at all. Okay, that's the cute thing about probabilities. As I give you more evidence, you suddenly start thinking some things might be dependent on each other. Okay, in this case, actually, is T independent of L up front? Yeah. Why? Because again, use the D-Sep criterion, and there is T, there is L. The only path between them is this. Okay, and in this case, it turns out that, let's see, T independent of, yeah. So here, this is a common effect. Abnormality is both an effect of tuberculosis and of lung cancer. Right? And so because of which, if I know one, so because of which, since this is not present, and nobody who is a descendant of this is present in the network, in the evidence, these are independent. Right? This is basically the burglary is independent of earthquake, given nothing at all. In that case, burglary and independent, earthquake will happen to be at the top of the network, but that's not the important issue. Okay. So then the next question was: is tuberculosis independent of lung cancer given dyspnea? Dyspnea. Yes, no. It's independent. No. Why? Because basically this path, this is a common effect. So neither this guy nor any of its descendants should be in the evidence. If they are, then it's not independent. So in the burglary alarm case, burglary, earthquake, alarm, Mary called, John called, right? Is burglary independent of earthquake given nothing at all? Yes. Is burglary independent of earthquake given John called? No. Because if John called, upfront it could have either been burglary or earthquake. But if you happen to know burglary occurred, then you have less reason to believe earthquake also occurred. Okay? So that's the whole point of that. So this one is not independent. Okay? Is X independent of D? Is X-ray independent of dyspnea? Why? No, basically because you go, this is the path. Remember the paths, you consider directionless paths and consider direction of the path only at the evidence node. Because in fact, in this case, look at this network. Your common sense tells you this cannot be independent of this because they are both caused by the same guy. If one is caused, then so is the other. Do you see what I'm saying? Okay? That's why, in fact, if you take the path, that's why I said consider the path first as an undirected path. And then only consider directions when you get to the evidence node. Okay? And at this evidence node, it's basically, so in this case, this is causing both of them. So this is common cause. So D-Sep will say, unless you give this as evidence, this path is not blocked. Okay? And then finally, is X independent of D given A? Yes. X is not independent of D by itself. It becomes independent given A. See the interesting contrast to T and L. T and L were independent given nothing, and they become dependent given D. Okay? And once again, all of these actually, you can make sense of it from a commonsensical point of view too. Because I actually gave you, the network structure, and you can sort of understand what is the causality here. Okay? What D-Sep allows you to do is answer these questions even if these were just, N1, N2, N3, N4, N5, N6, N7, N8, which is what your program sees it as. It doesn't know the actual semantics of these words. Okay? So then finally, is V and S independent of X given A? Is visit to Asia and smoking independent? So these two together must be independent of X-ray given A. What? So V and S, the only way you can go from V and S to X-ray is what? What are the paths? So here is one path. That is blocked. here is another path that is also blocked. Okay, but here is a third path. Is that blocked or not?
Yes.
What do you say? Is this blocked or not?
Yes.
Why?
Because both the arrows
So at the evidence node, the arrows are common cause. Okay, and both are caused in essence by the same. This as well as this. This becomes a common cause, and so once again it's blocked. You see what I'm saying? Okay. And how about is Vs independent of xd given A? No, because this time you need the bronchitis to be given. Otherwise, not all paths are blocked. Okay. Now the interesting thing is, first of all, you learned something abstract about conditional independence assertions that hold in the network, and secondly, you learned essentially that a network has exponentially many conditional independence assertions. So writing them all down makes no sense. So what you instead you do is you provide the topology, and you know that D-Sep will get you all the conditional independence assertions as and when you need them. Most of the time, you never really need to compute these yourself. Okay, so the last part of last class and this part, this is kind of good semantic understanding of how the conditional independence assertions hold in the given Bayes network. But in using the network itself, pretty much the only thing you need is the understanding that a node is independent of its non-descendants given its immediate parents. That's the only thing that you really need. Okay, most of these other independence assertions, these are actually used in designing algorithms. Since if you never want to use if you never want to actually design an algorithm and let somebody else design the algorithm, you don't need to know this stuff. So in designing an algorithm, if an algorithm is taking certain steps, then you need to justify them in the context of these independence assertions. But from a semantics point of view, it's beautiful to realize that given network corresponds to a whole bunch of independence assertions. And actually, that brings you to a more theoretical topic that I won't go into too much in this class, which is essentially, if I were to tell you that the network I have in mind, that the joint distribution I have in mind, satisfies exactly this set of conditional independence assertions, no more, no less. Will you be able to make a network that captures exactly those many and no more and no less? Do you see what I'm saying? So generally, if I have a certain set of conditional independence assertions that I do know the domain has, a network may or may not support it. Okay? If every assertion that you have that you know for sure is holding in the network, in the domain, is also holding in the network, okay, then that basically makes the network be more efficient because it's actually exploiting the independencies. If on the other hand, network is making more independence assertions than what you said, then it is actually unsound. Right? So for example, it turns out if I were you, suppose I want all of these to hold, all of these to be holding. Okay, it may sometimes be the case that I can just give a network which is disconnected components. Just everything is independent of everything. If everything is independent of everything, then all independence assertions will hold by definition. So one way the network can capture the assertions you gave is say, this is true. But then that would mean that it is making more independence assertions than you actually said are holding. So then the question becomes, theoretically, if I give you a set of independence assertions, can you always write a Bayes network configuration that captures exactly those assertions and no more and no less? The answer, it turns out, is what? What do you think it would be? It's unfortunately no. Okay, that means if you actually give a set of independence assertions about your domain and say only those hold, no more, no less, and give me a network that captures exactly that, sometimes I will not be able to give you a Bayes network at all. Okay, so either I have to do more independences or less independences in the network than what you are expecting. If I must do one of them, either I should assume more independence in the network or less, which one should I do? Less. Because less, you can't go wrong. Did you see what I'm saying? When in doubt, assume more things are dependent on each other. That way you'll wind up having to get more probabilities, but at least you will never say wrong answers. So some Bayes networks are good enough for us in the sense that given any set of assertions, you'll always be able to find a network that's like a close enough match. That means it captures, most of them. And it doesn't do any more additional assertions that don't hold here. But if you want exact match, that's not enough. Because of which, if you were to take other courses on this area, you will also hear of something called Markov networks. And Markov networks would be essentially non-directed graphical models. Okay, and they turn out that they also are not complete. So that means there are assertions that they can't capture. But between them, both of them together, you can capture one. Okay, that's just sort of a peek. But the practical impact of this is negligible because, when in doubt, you can always, if you're not sure, just assume that they're dependent. Okay? Don't assume they're independent because that way you can go wrong. Does that make sense? Okay. Okay. So, next thing I want to do is start talking about inference on Bayes networks. And I'll keep this board for a bit because I'm going to write on the thing. So you have a Bayes network like this, and I'm going to ask you a question. Give me probability. You already know this. You asked me, you were trying to give me the probability of V not T, S not L, A, B not X not D. How did you compute that, by the way? That is, you would just say, not X given A, right? P not X given A times P not D given, say not D given A and B. Good. Okay. P not and P A given not L, not T. Good, you got the hang of it. Times P L P T given P not T. Yeah, that's what I wanted. Not T given V. Okay, times P not L, right? Not L given S. And then this, we forgot this guy. Bronchitis, PB given S. Okay, if this stuff doesn't make sense to you, you're not understanding Bayes networks. This is the second time we are doing in the class, and you should be able to just read it off and take any joint probability and split it into numbers. The good thing about this is all these numbers are available in the CPTs here. And you also figure out how many CPT entries we need, right? So you need what? 1, 1, 2, 2, 2, 4, 2, and 4.
Shouldn't the probability be multiplied by P of V and P of S?
Oh, yeah, sure, I'm sorry. Yeah, P of V and P of S. Okay, and so you would basically, in fact, every joint entry would be computed by picking an entry off of each of the CPTs. if you didn't ask somebody that, that's pretty much what you kind of see, that we are not looking into these guys' numbers at all. Why did we give them? It makes no sense. Okay, again, so in this case, 2 plus 2, 4, 6, 8, 12, 14, 18. So 18 probabilities you have to give, and then you can convert any joint distribution, joint probability entry into this. And once you do that, then essentially you can compute, in essence, you know how to compute the entire joint distribution, and so you should be able to compute any probabilistic query. Okay, the trick, of course, is that some queries should take less effort than first converting everything into joint distribution and then answering it. Do you see what I'm saying? Okay, this is the same issue that we faced in the propositional logic. If I give you a bunch of statements like, A implies B, B implies C, blah, 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 and D100 implies B101, and then blah, 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 and B100 is true, blah, blah, blah. Okay, you can always, and I want to know, is D101 true? Is it entailed? I can always answer this question by doing a big truth table. Okay, if there were about 1,000 variables, I just need to write a truth table that's of size 2 power 1,000. It will be big. And then you will be able to answer this question. Right? But that's kind of wasted effort. Because really, if you just use model exponents, you would be able to just use this and this together. You can directly derive D101. And that's basically, in the worst case, entailment computation is exponential in propositional logic. In the worst case, computation of a joint, any arbitrary probabilistic query in a Bayes network is exponential. But just because something is exponential in the worst case, you don't have to always do exponential amount of work. You need to be able to do better if, in fact, the problem at hand actually needs less effort. The particular query at hand needs less effort. Okay, much of what we'll try to do in improving, so the zeroth idea for Bayes networks is essentially, given a Bayes network, we can always compute all the joint entry distribution, the entire joint distribution, and have it ahead of you, in front of you, and then you can answer any query. And you know that, right? Any random query can be answered by just summing up entries in the joint distribution. And any conditional query can be done by summing up entries to get the numerator, summing up some other entries to get the denominator. And the numerator by denominator would be your conditional probability. Okay? So this one, essentially, this way of doing it first requires you to enumerate and keep the joint probability distribution somewhere. And it's good if, in fact, forever and ever after this, you will be asked questions only on this network. Okay? Because you may as well just compute the joint distribution and keep it around, and then people keep asking questions, and then you just answer them. So it's like, my analogy for this is, if you have one potato to bake, you would use microwave oven. You have 100 potatoes to bake, you don't use microwave oven. You get an industrial-sized oven, or put your house on fire and put potatoes in it. Either way, they'll get done. Okay? So the idea is the upfront work would basically be amortized. If you keep asking queries, if you keep giving more and more potatoes to bake, you may as well just basically start the conventional oven, wait for about 2 hours until it becomes 400 degrees, and then put all your potatoes once. Because if you have just one potato, you won't do it in conventional. So going to joint distribution or going to the truth table is the conventional oven idea. Okay, and going directly to either proof theory or the stuff that we'll be discussing for Bayes nets, that's essentially trying to see if there's a shortcut for the specific query at hand. Okay, so that's the background. So given the joint distribution, we can always answer any query. So we can do inference on Bayes networks. So you should not be surprised that you can do inference on Bayes networks, right? Can we do better? As I basically said, you can implicitly enumerate only the part of the joint that is actually needed. Rather than compute the entire joint distribution and then start summing out stuff. Okay, as a classic example, suppose my query was what is the probability of tuberculosis given visit to Asia? I can answer it in my way, which is compute the entire joint distribution, which will have 1, 2, 3, 4, 5, 6, 7, 8, 2 power 8 number entries. And then, sum away the numerator stuff, sum away the denominator stuff, and I'll get the answer. What should you have done instead? You should have just read it off from the table. It's right there. Would you get the same answer both ways? Yes. If not, you're in big trouble because you wasted like 2-3 weeks of your life, learning inconsistent theory. Okay? It will be the same answer, but in this case, reading it off will be much nicer, much easier. You see what I'm saying? And similarly, by the way, if I don't ask you that, but rather ask you probability of V given T, what do you do?
Probability of V.
What is probability of V given T? Is probability of T given A times probability of A by probability of T. You know this number. You know this number. Right? I mean, so V given, why did I start getting A? I'm sorry. V given T is T given V times PV by PV. Right? You know this number. You know this number. Right? But then you don't know this number. It looks as if you are sunk, because to get that, you have to again go back to the entire joint distribution. Right? But here's another idea. Suppose you also computed probability of not V given T. What would that be? That would be probability of T given not V times probability of not V by probability of T. Okay? Right? Now, suppose I consider 1 over P of T equal to alpha. Just make it alpha. Right? Then I can say this whole thing is alpha times this, and this whole thing is again alpha times this. Now, what can you do now? What should these numbers be? If you add them up, it should be 1. And this, so suppose this kind of became 0.7 here and 0.4 here. Okay, then 1 equal to alpha times 0.7 plus 0.4. So alpha equal to 1 over 1.1. Do you do magic? Right. So I got away without actually doing P of T. This is a beautiful trick. We just assume you can always use it. This trick is called normalization trick. What did you do? You don't get something out of nothing. Okay? If you are actually, I originally only asked you what is P V given T. But if you also go ahead and compute P of not V given T, then you know that those two should be added up to 1, and so from that you can compute alpha. Most of the time, people actually are interested in asking you distribution queries. Nobody asks you what is the probability of V given T. They want, remember that picture I said in Bayes networks, we're always interested in posterior probabilities. So there is a prior probability of V positive, V true is this much, V false is this much. And with the evidence that tuberculosis actually is there for this poor guy, what do you think is the probability that they actually went to Asia? That will again be posterior. You again want the entire distribution. For the Boolean case, distribution is very close to just one value because there are two values in the distribution and you are anyway computing one value, you can compute the other value, you're done. Okay? But if this was multi-valued variable, you'll actually do some reasonable amount of work. Suppose it turns out that the visit to Asia, is not true-false variable, but it has 15 possible values. Then you will have to actually compute each of the values of V given T, and then you add them all up, and that would be equal to 1. But still, it turns out that's better to do than actually trying to compute prior probability of tuberculosis, because that might just open up the entire Pandora's box of having to compute the entire joint distribution. You see what I'm saying? Okay? So you should be happy that you can do this in this case. Okay? But this idea of normalization is something that we'll be actually using all the time in actually deriving algorithms in a minute. But this idea you should understand. Okay? So at the expense of computing the distribution, you don't need to compute the denominator of the Bayes rule. I used Bayes rule here. You guys realize that, right? I did PAB in terms of PPA. Okay, and at the expense of computing the distribution, I was able to avoid having to compute, in terms of medical terminology, you are asking essentially probability of symptom, probability of disease given symptom. Given that you had probability of symptom given disease. Okay, and the Bayes rule will require you to figure out probability of symptom. That's harder to get. Normally, medical textbooks have probabilities of diseases, probability that the disease causes the symptom. Probability of symptom is harder to get, but you don't need to get it. If you were to compute the distribution, then you can normalize that out. And this is called the normalization trick. Okay, this is just from elementary probability theory, but we will use it all the time. And any time I need to, let's say, if I say I need to compute PB given A, I'll write this as PPA by PA. Right? That's correct. That's the definition. And then I'll say, which is alpha times PPA. Because my assumption is, you can figure out that alpha by computing not just, if you compute the entire distribution of B given A, that means B true given A, B false given A, then from that you can figure out what the alpha is. Okay, so I'll assume that's what we'll be doing. Any questions on this? Okay.
What
Yeah.
is the probability P of T 1.1?
1.1.
What?
P.
The probability of PT will be 1.1. So the wrong example.
Which one? I don't understand. What is
The alpha is
example
1
the
by.
wrong example, which is 0.7 plus 0.4 is 1.1, and when you get the PT, it will be 1.1. So PT can't be 1.1.
Oh. No. No. All I'm saying actually is, I don't know, maybe these numbers will come to something, and when you add them up, and one by that will work. That's for sure. I guess I may have introduced inconsistency, but probabilities, the Bayes network won't introduce inconsistency. Okay. Okay, so that's done. So now you have two ideas. You can already do some exam questions with this, right? I mean, imagine I can give a random Bayes network and say, find out a particular joint probability distribution. You know how to do it. I can ask, give me one of the numbers that is actually present in the network. You should be able to know how to do it. I know life is not about exam, but at least you know something. Okay, and then I can ask you the opposite one. You can still do it. But But what I really want to do is not to make you, pass the exams, but get a single algorithm that will just do it for any random query. That's what we're trying to figure out. Okay. Let's see. Let me skip over this and come back to it in a minute. But let me do this first. Okay. The basic idea that I would want to use in computing these probabilities, the simplest idea, no, it's not the 0th, but 0.1 idea for computing probabilities using a Bayes network, is essentially just what I wrote earlier. So for example, if you have this network, burglary, earthquake, alarm, John calls, Mary comes. Okay, and I want to compute the probability of B given J and M. Now notice that I'm asking directly the distribution of B. The capital letters assume I want the distribution. Small letters assume that is the valuation. J small means John definitely calls. And M small means Mary definitely calls. So what I'm saying is, give me the distribution of burglary true and burglary false, given that John called and Mary called. Okay, that's the most general kind of questions I'll ever ask on Bayes networks. And that would be nothing but BJM by BJM. Right? That can just be written as alpha times P BJM. Okay. And now the interesting thing is in trying to compute, remember B basically here, this is actually, it's not just a single probability. I need somehow to get this from this, I need to get two probabilities for B true and B false. So I'm essentially manipulating what are called factors. That's why I'll go back to those previous slides and show you a little more about what the factors look like. But essentially this is some matrix of numbers. Okay, so which we are basically telling you what you're trying to compute here is what's the probability B true and J true, M true, and also what's the probability B false, J true, M true. Okay, now what to do this, you want to go back to the joint probability distribution table. But the joint probability distribution table won't have BJM entries. It has BJMEA entries. You need to get rid of E and A. How do you get rid of variables in the joint distribution? You sum up entries. So what you really need to do is you say BEAJM, the probability BEAJM, okay, where A and E are summed over for both the values. And you will get one entry out of this with B equal to true, and another entry out of it with B equal to false. That's it. So you computed directly the distribution in one fell swoop. This is very easy to understand for single numbers, but essentially what you're doing is you're computing distributions together as factors. And to get that idea clearly, okay, I want you to think of this problem. Okay, so start with a very simple network. A causes B and C. Okay, and unfortunately you can't see. I'll just bring it down a little bit. Okay, that's fine. Anyway, so I think I'll leave it like this. This can be seen too. 0.7 for the prior probability of it, and then B given A is 0.3, B given not A is 0.8. Okay, and C given A is 0.45, C given not A is 0.6, 0.55. It should be 0.55. Otherwise, I just no. It's sorry. PC given A is 0.45, PC given not A is 0.6. They don't have to add up to 1. Right? Okay? Correct? So that's my network. Now it turns out that I really want what I really have given you is this, implicit. Okay, this was an implicit representation. If you extend it, then you have a little table. Think of these as like database relational tables. How many of you have done databases? Okay, do you know join operations in databases? You're going to be doing join operations like that. Okay, that's what you'll be doing. You have things like matrices, and you act as if you're multiplying matrices, but you really will be doing join operations on tables. Okay, that becomes clear in a minute. So I have a little relation here which says a.7 not a.3. Okay, and then basically that's the a.7 has been converted to a.7 not a.3. And then similarly, b given a.3, b given not a.8, I just write it as a and b is 0.3, a and not b must be 0.7, because those two conditional probabilities have to add up to 1. Right? And not a, b is 0.8, not a, not b is 0.2. And then similarly for this. So now I have 3 what I call factors. Okay, 3 factors. And so basically I have, there's a factor there, there's a factor there, there's a factor there. Okay, a factor is essentially, a set of valuations for variables and a number. The factors don't necessarily have to correspond to probabilities. For example, this factor corresponds to a conditional probability. This corresponds to a prior probability. Later on, somewhere in between, they may not correspond to anything. Okay, but the interesting thing is, you can see what you do in computing the joint distribution as multiplying these factors. At least that's the analogy I was getting you to agree with me last time, right? That I was saying I have 32 in mind. I gave this guy 4 and an 8, and I gave this guy 16 and a 2, and so on. So somehow factors multiplied will give you the joint distribution. Okay, I said that. But now I'm actually going to show you what I mean by factors being multiplied. I define a particular multiplication. Okay, so that if I multiply this times this times this, I will get the joint distribution directly. I mean, you have this in your head. It's just I'm making it explicit so that we can do the discussion of the algorithms without getting into confusion. Okay, so what do I do? Now, if I need the distribution A, B, C, which is basically the joint distribution, I will write it as P of A times P of B given A times P of C given A. Right? This is what you were doing before too, except you are using this for individual entries. Now I'm going to use the same thing to compute the entire joint in one fell swoop. Okay? So if I'm multiplying this by this, I'm multiplying A.7 not A.3 with A B 0.3, A not B 0.7, not A B 0.8, not A not B 0.2. All I do is I join those tables. What is join? You essentially, basically, in this case, this row can be joined with any row which has A in it. And similarly, this row can be joined with any row that has not A in it. Natural join, right? So if I combine this and this, I will get A, B, and I will get 0.7 times 0.3. And then similarly, A not B would be 0.7 times 0.7. Right? And similarly, not A, B is 0.3 times 0.8, and not A, not B is 0.3. Okay? At this point, you actually have, what did you compute by now? This factor actually has probabilistic semantics. Because this factor was P of A, this factor was P of B given A, so this factor is really P B A, the joint. So if you only have questions on B and A and nothing else, this is your man, or woman, whichever. Okay? And then you just essentially, if I want to know what's the prior probability of B, P of B. I take this factor and I add up this entry and this entry. I get P of B. And similarly, if I add these two guys up, I get P of not B. Right? Okay, but I'm not going to stop here. And then so I multiply this by this, I get this. Now I multiply this by that. And I do the same thing again, join. Okay? So for example, I can join AB with AC, I will get ABC. The previous join was one of those things where actually you didn't see much of a difference in the next entry. But here, AB is being joined with AC, you get ABC. AB can be joined with A not C, you get AB not C. So each entry here gives rise to 2 entries in the table. So not surprisingly, you will get 8 entries, which are the 8 entries in the joint distribution. Okay? So that's your joint distribution. And I did that just by doing the join operation. I mean, this, you can't call it join, but this is, the factor multiplication is very much like, they call it point multiplication, typically. But point multiplication, I think, is closest to your idea of join. And you compute the join relation and then multiply the numbers corresponding to those 2 entries, and you'll get the probability for that entry, the number for that entry. And what you get here sometimes actually have probabilistic semantics, sometimes they don't. But in essence, when you are multiplying these CPTs around, you are essentially going through computing these kinds of tables. And you call them factors. And I just showed you how I multiplied factors to get the big joint. This is your real joint distribution. And I just showed you that this is multiplication of those 3. That's what I mean by saying Bayes network factorizes the joint distribution. Okay? Then the other thing is variable elimination, which is summing away. So at any, you can either wait until the last minute, or in fact, as soon as you computed P of AB, if I asked you what is P of B, you would just have to eliminate A from the joint of P of AB. Right? Okay? And if I eliminate A, all that means is I sum the rows where A changes polarity and everything else remains the same. Okay? So for example, I'll get basically this and this are added up, this and this are added up. I'll get a 2-entry table. One would be P of B, one would be P of not B. Okay? So all you need to know to deal with Bayes networks is handling factors. You multiply factors and you variable eliminate factors. So given a factor and a variable, you can eliminate it by essentially adding up the rows where all that changes, the entries of adding up the rows of the table where all that is different is the valuation of the variable that you're trying to eliminate. If it's true, false, then typically you just want one is saying A and one is saying not A. Okay? Fine? Now, the interesting question, of course, is from the point of view of, I said some questions should be answerable easier than without having to compute the entire joint distribution. So you just sort of saw that had it been the case that the question I asked is, probability of B, prior probability of B, you could have answered it after this step. You didn't have to go all the way to this step. If you went all the way here, you have to come back again because you have to then eliminate the variable that you introduced for no good reason. So in essence, what happens in these kinds of computations is you start with the small factors, which are the original factors in the network, and you multiply them. One way is multiply them all first, and then start eliminating. That way you will get the entire joint before you start doing anything. And that one basically will have essentially constant time. Basically exponential time. That exponential time is just to compute the entire joint distribution, plus whatever little eliminations that you have to do afterwards. Okay, but another way is only go up to the point where you just need to answer your query. So in this example, if I just asked you P of B, going all the way there and coming back would have been a wasteful effort. And that's what more interesting algorithms do. And then going all the way here would make sense if in fact you're going to be stuck with this network for about 3 years of your life. Right? In which case you may as well just keep this instead of trying to ask every time what's the best way to, what are the things to multiply. Okay? And so given this background, I can now go back here and understand what I just did here. Right? What I did is I tried to do B, J, B, the probability of B, probability distribution over B given J equal to true, M equal to true. Right? I wrote that as P BJM by PJM. I wrote that as alpha times P BJM. You need to feel comfortable with this step. You should be able to always understand that. And that was what I was doing when I showed you the normalization. Okay? It's just that I can always get away without doing the denominator because denominator is same for everybody. And so, it's assume it's alpha and then, normalize it later. Okay, that's the normal trick. Okay, so now any query I have will ultimately be like this, alpha PBJM, approximately like this. Some sort of a joint, some sort of a half materialized joint. Okay, materialized in the sense I already said J must be true, M must be true. And only B gets to change. Okay, and so then except I can't read off these entries. I know that I will be looking for entries where J is true, M is true. And then, but what else? I need to know about E and A, so I sum over E and A. Okay, when I do that, now I have the entire joint distribution there. Now it's not the case if I have this, and if I already computed the entire net distribution, I can just read it up from a table like this. And this is for 3 variable, but there will be one for that bigger one too. But one of the I said this is a 0.1 idea, not the 0th idea. Because really it doesn't ever make you compute PBEAJM. The probability of BEAJM, the entire distribution is never computed. You never computed the 32-row factor. Instead, you essentially are computing just these numbers. Okay? So what would you be looking for? You would be looking for E true, A true, J true, M true, and B true, and then E true, and then keep B true, and then E true, A true, J true, M true, E true, A true, A false, Q true, and false, true, 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 false, false, true. So they are like keeping T everywhere. I will have 4 entries. All of these can be computed by actually just your normal trick, because those are individual probabilities. They can be computed by looking at the network configuration and multiplying and getting that split into. So for example, if I ever need PBEAJM, it will be PB times PE times PA given BE times PJ given A times PM given A. Right? Now, the interesting thing is actually, I could look at this essentially as computing one value for B at a time, or I could look at this as just computing the entire distribution in one fell swoop. In which case, I view these as factor multiplications. Okay? This is arithmetic. It's not, under the guise of doing probabilistic reasoning, we just have to ultimately figure out how to do some arithmetic over these distributions. Okay? Fine. So you can do this, right? This is better than the zeroth idea because it's never computing the entire joint. It's only looking at the entries that it needs, and it's computing them on demand. So it's 0.1 idea. Okay? The problem with this 0.1 idea is that you can actually, it turns out that you can do this by, to understand what it is doing, you should look at this picture. So that's one entry, computation of one entry. Okay? What it's doing is multiplying P of P times, here is P of E, this is P of not E, and then here there's a branch, these two branches add up, and then get fed there, these two branches add up, get fed there, they get multiplied by this, and the answer comes out. That's your flowchart. That's the arithmetic flowchart. Okay, now let's talk about space and time. Okay, space, if you do this in the depth first fashion, if you look at this tree in the depth first fashion, you can get by with, B times D space. Time, on the other hand, essentially, in the worst case, you will do exponential number of multiplications and additions. This idea you should understand. If nothing else, you should understand this idea at least. Zeroth idea, anybody understands. This you should understand. And the next idea, which I will introduce today, and we might talk a little more about next class, but I'll also ask you to, pour over an example, write a, worked out example, is doing this more efficiently using the idea of dynamic programming. How many of you have heard of dynamic programming? What is the basic idea of dynamic programming?
Store intermediate.
What?
Store intermediate.
Exactly. Store intermediate computations so that you don't need to recompute them again and again and again. Now, for that to happen, for that to actually be a winning idea, it must be the case that without dynamic programming, you are multiplying same things again and again and again. Here's a picture. Can you show me some multiplications I'm doing repeatedly? Right? See? How many times do you want to do this multiplication? You think second time it will change maybe? Right? Okay? And then similarly, this multiplication. You do it twice. You're doing operations multiple times. Okay? Somehow you should avoid doing those operations multiple times. That's basic idea of dynamic programming. And what you do is, I'll tell you in a minute, but essentially it's a summation and you do the summation bottom up rather than top down. And so you evaluate this tree bottom up and keep the intermediate results so that anybody else wants that same result, you don't need to recompute it again. Okay? And on top of that, there is another interesting point, which is that, so this idea that I was saying, which is dynamic programming idea, it's called the variable elimination algorithm. Of course, everybody is doing variable elimination, but for some reason, this is called variable elimination algorithm. And you know that pretty much all you do is eliminating variables here. This is the old idea. This is the 0.1th idea. It eliminates variables. The question is, the summation is being essentially done left to right. I want you to do it backwards, in essence, to do dynamic programming. Okay. The other question is, what order do you eliminate the variables? You can eliminate variables. So if I do summation over E, summation over A, I can, for example, first sum over A, and then basically simplify that table, and then only do the other operation for the simplified table. Okay, and that essentially will reduce the size of the factor that you will keep in the memory. So the optimal order, if you do these variables are eliminated in the optimal order, you will do the least amount of work. But if you do it in a good order, in a reasonably good order, is to eliminate the variables in the topological order. If you do that, then typically you wind up doing less amount of computation, because the size of the factors that you compute in the middle, is bounded. Okay. So that's the idea of variable elimination algorithm. And this is the slide that actually mentions that. And what we are saying is that you are going to compute factors and store them so that next time around, so you store them in memory, and so that next time around you need entries from that, you don't recompute it. You just have it already. It's been computed. Okay? And what you are computing, of course, is some multiplications of tables. And then after a couple of multiplications, you might eliminate a variable, so then you'll get a smaller table, with fewer columns, right? But all of these, they are not necessarily probabilities. So you just call them factors. All we know is in the end, the factor that you are left with would be a probability, because if you are asking a probabilistic value. And the beginning, the factors are conditional probability tables. In fact, it turns out that factors in Bayes network are at least have initial factors in Bayes network have probability semantics, because they are either prior probabilities or conditional probabilities. Okay, but I mentioned this other idea called Markov networks, which we didn't go into. There, in fact, factors don't even have probabilistic semantics. They're just numbers. The initial factors themselves don't have probabilistic semantics. Okay, all that we care is the end, you get a joint distribution, which is probability distribution. Okay. Anyway, so here, go back to PBJM, and I'll write this as alpha times P of P. Now remember that I wrote this previously as this. Right? The interesting point, of course, is if I'm going to sum anyway, so here I'm basically getting an entire joint entry and then summing them. But each joint entry itself is a multiplication of factors. So you can actually take the summation inside the multiplication, so that there will be fewer multiplications that you do overall. That's the basic idea. Okay? And so, in this case, I will write this as PBJ given M. And remember, the picture looks like this. It's a useful thing to remember. Burglary, earthquake, alarm, John calls, Mary calls. That's the picture. Okay, so I'm doing this, and I would write this essentially. I'm doing in terms of, I'm computing the distribution for B. So this P of B times, I have to eliminate E. Now the elimination of E was in the before this, originally, right? But E doesn't affect what PB's value is. So you take this inside. You see what I'm saying? And actually, you take the A up to here, because these three factors depend on alarm. Okay? So you multiply these sum over A, I'll get a big factor. Okay? I will then multiply that with P of E and then eliminate E. Okay? And then after I eliminate E, then I multiply it by P of the prior probability of P, then I will get what I need. Okay? So that's basically the algebraic manipulation that's being shown there. So alpha times, so in this case, you can actually remember that each of these themselves can be, if you're writing a program, you don't need to decide when do I call something a factor. You can call any intermediate result a factor and store it. And the storage would be dominated by the large factors. Okay? So you have, this is your A factor, this is your J factor, this is your M factor, and so what this is being shown is I remember the M factor first, then I multiply the M factor by this, and I will get two other factors, F of J, F of M, and then I am multiplying it with this. Okay? And then I'm keeping this whole thing in as a single factor. By the time I came here, I have summed out A, because after I multiply those three, I get to sum out And then when I summed out A, then this is a factor that's only in terms of B and E, because A has been summed out. But it really does depend on A, J, and M. Okay? And then you then multiply that by B of E, and then you eliminate E. Whenever you sum, you eliminate a variable. Okay? So these factors, these intermediate factors, you store in the memory, so that you don't have to recompute those numbers again. This is basic, arithmetic trick, dynamic programming trick. Okay. As to how fast this would be with respect to this particular idea, the simple idea, depends on how big are your factors. How big are your intermediate factors? And how big the intermediate factors are depends on the order in which you are eliminating the variables. Okay? Notice that in this case, the elimination order was you eliminated alarm first and then earthquake. Okay? So again, that's again reverse topological order. That normally works, but that's not guaranteed to be the optimal order. Finding the optimal order of elimination turns out to be as hard. It's one of the sad parts. Finding the optimal order of elimination such that variable elimination algorithm does the least amount of work is NP complete. So mostly people will do a heuristic, which still does better than the dumb idea. Okay, this essentially, and again, in multiplying this, is essentially these sort of factor multiplications. This is what the textbook described as to what factor multiplication and eliminations are, and I described them in this example. They're basically the same idea. Okay. I will also send you a worked out example so you can look over it to make sure that what is being stored, what factors are being stored. Okay. Both of these that we looked at today, the 0th idea, 0.1th idea, and the first idea, which is the variable elimination, all of these compute the probabilistic query that you are asking for exactly. They'll compute the exact number. Next class, when we come, we will actually say, why do I want to compute exact numbers? These are probabilities, these are numbers, so I can estimate them as close as I want. One idea, for example, is if this is a network, I can then sample this network to get the joint distribution. Okay? And then from the samples, I can just essentially see in how many samples is B true. That would be the prior probability of B. Or in how many samples where A is already true, B is also true. That's the conditional probability of B given A. Right? So that would be the idea of just sampling the network and generate more and more samples. And the more samples you generate, the more accurate your numbers would be. We will talk about those because, in fact, it turns out that the exact inference on the networks for large-scale networks is essentially infeasible. Whereas approximate inference, which is using samples, you can decide how accurate you want, more versus less number of samples. Okay, so we'll talk about a series of sampling algorithms for inference, and then we will move out of basic.